Today we're getting into the final module of this class. It's another two-part module, all about controls. So when we're talking about controls, I mentioned this way back on day one, but we haven't really had a good chance to revisit it yet. But it's this idea that how your equipment is controlled is way more important than just the raw efficiency of the equipment. Some basic examples: you have a chiller with an efficiency of 20 EER. That's a very high efficiency chiller, but if you're operating that in the winter for no reason, you're probably wasting a lot of energy on that chiller. Or if you have a pump controlled with a VFD, that's good in theory, but if you don't have the control algorithm and the programming in place to actually use that VFD to vary the speed, whether you don't have it or it's done poorly. I mentioned earlier when we were talking about VFDs, some maintenance personnel, they hear about how great VFDs are for saving energy, but it's only going to save energy if it's being used properly. If you just put a VFD on a motor, that could actually cause you to use more energy if you're not using the VFD properly. Or if you have HVAC system with great controls, brand new, state of the art, good in theory, but if you're running everything 24/7 when nobody's there, that's not good. And controls, they're often misunderstood by a lot of maintenance staff. You'd be surprised at how many people get put in charge of HVAC equipment when they really don't have that great of an understanding of how the equipment is supposed to work. A basic residential gas-fired furnace, like you'd have in your house, that is a very simple piece of equipment. Most people can understand how that's supposed to work. But when we get into commercial equipment, where we have VAV systems or VRF or multi-zone units or dual duct systems, there's a lot more complexity going on in that type of system. And if you don't know what you're doing, that means you can't optimize that equipment, or maybe you just don't really care that much about it, or maybe the people are comfortable in the building. Well, that's good. That means you don't get phone calls on nights and weekends when people are working, but you still might be wasting all kinds of energy and spending thousands of dollars that you shouldn't be. So the bottom line, controls are a huge deal. If you're an energy engineer or a design engineer, you need to be the experts on it. As a energy engineer, we are mainly concerned about modeling energy savings. As a design engineer, we need to be wary of the control sequences that we write, because we write how that equipment is supposed to run. And it's not only an energy issue, it's a potential operability issue. Or if you write poor control sequences, you might not be able to get all of the heating or cooling out of the system that it's designed for. For example, what if you write your sequence in a way that causes simultaneous heating and cooling, where they cancel each other out? That normally would be a bad thing. There are a couple main types of control systems. There's three that we're going to talk about today. There's pneumatic controls. With pneumatic controls, your equipment is turned on and off using a pneumatic tubing network powered by an air compressor. So you have this air compressor in your building that's producing compressed air, and then that gets routed through the entire building through a whole spider web of pneumatic tubing. And all of your control signals are based on a varying pressure. The way they do that is you can take a pressure output And you can convert that to something else. As an example, a temperature reading through pressure transducers. As an example, let's say you have a pneumatic thermostat that's controlling a hot water control valve. Because remember, the thermostat is the device that is telling your heating system when it needs to turn on. So that thermostat needs to control your hot water control valve in some fashion. The temperature reading, so the active temperature of the room that that thermostat is in, a pneumatic thermostat can take that temperature reading and convert it to a corresponding pressure output. So if you have a low temperature in the space, that could mean your thermostat will output a lower pressure, a lower PSI on the output side. And the hot water valve knows that means I need to open the valve more and get more heat. So ultimately, a low temperature means open the hot water valve, and it does that through this intermediate pressure output. And on the other side, if we have a higher temperature, that could produce a higher pressure output, which would then tell you to close your valve. Here's a basic schematic of a very simple pneumatic control system. So we have our air compressor at the start of this process. And this is the thing that kind of makes this whole system work. That air compressor is producing about 30 psi compressed air through this tubing, and you can see it goes through an air dryer and goes through a filter station before ultimately getting sent out into the building to all of your end devices. And the black lines here, so that would be the pressure input going into your end devices. So this would be a thermostat where that's taking in 30 psi, and that's an approximate value, might not be exactly 30 psi, but the point is it's taking in a higher pressure on the input side, and then it will vary the output to some range, say 3 to 15 psi, and that would be the red right here, based on the temperature it's reading at this thermostat. So it could be when this thermostat reads a low temperature, it outputs closer to 3 psi. That sends a signal to this hot water valve, which then tells the hot water valve to open. Or if it's reading a high temperature, closer to 15 psi is what would be output, and that would go to the chilled water valve, which would tell the chilled water valve to open because we need cooling. And so these valves would essentially work inverse from each other. Even though they're receiving the same signal, you can set up the device to say, start opening this valve at 7 psi and it should be fully open at 3 psi. And then this one, start opening it at 8 psi and it should be fully open at 15. And so you could have each valve respond to a different part of this range. So yeah, the pressure output will vary from the thermostat based on the space temperature being read right here. You could have also a temperature element that's monitoring the supply air temperature, assuming this is a cross section of a duct, and we want to know what's the temperature of the air moving through this duct. So we're still sending that 30 psi into that sensor, and then depending on the active reading, that will change the pressure output, which will then go to a temperature gauge, or I guess a thermometer would be another term for it. And this is a very simplified system. A typical pneumatic control system would be going to hundreds of end devices. There'd be tons of thermostats and temperature readings, all kinds of stuff, just this massive network of pneumatic tubing going to all kinds of stuff in your building. And this is an entirely mechanical control system. It's all based on pressure and pneumatics. There's really no electronics going on here. And this is one of the first generations of building automation controls. When they started to try to figure out how can we automate an entire building's HVAC system, this is what they came up with. And it was very useful in its time. Today, we don't see a lot of pneumatic controls because we have newer and better control options available. So very few new construction projects are going to use pneumatic controls, but there are some special circumstances. But as an energy engineer, we still see a fair amount of these in operation in older buildings. We've done many projects at McKinstry where we've torn out old pneumatics and put back in a better control system. So as an energy engineer, uh, kind of similar to when we were talking about multi-zone and dual duct systems, we don't really see those in new construction, but we still see them in existing buildings, and we still need to worry about how do we retrofit those. There are some advantages of pneumatics. This one's pretty rare, but it can happen. It can be useful in spaces or buildings that require explosion-proof equipment. Because there's no electrical components, it's all mechanical based, nothing can make a spark, nothing can explode. That would be a uh, pretty rare instance, but those cases do exist. And because it's entirely mechanical, if something goes wrong, maintenance people might have an easier time understanding what's wrong. A lot of the old school HVAC technicians still aren't really on board with the newer control options, but they can look at an old pneumatic system, and because it's all mechanical, they can work their way through where is my problem. So they might have an easier time figuring out what's wrong. But they can be a maintenance headache for those same individuals. They are prone to leaks, and they still can be difficult to troubleshoot. I'll show you a picture here that might help illustrate that in a moment. And this does require a big old air compressor, which does use a ton of energy. Air compressors are one of the least efficient devices that we'll ever see, and I'm not sure what it is about the technology that they just haven't gotten much better over the years. But uh, I think it's about only 1/7 of the input energy into a compressor actually turns into something useful, and the rest of it just goes straight to heat. And generally, it does offer some pretty poor capabilities compared to the more modern systems. And there's not that many experts left who really know these systems all that well. We still run into these old HVAC techs who they swear up and down that pneumatic controls are the way to go and they don't want to bother with the new stuff, but those people are largely retiring. And if you need to troubleshoot an existing pneumatic system, it can be difficult just to find someone who's got the knowledge to work on it. So this is a pneumatic control panel. So this is awful. I mean, trying to figure out where all this stuff goes would be an absolute nightmare. But you can kind of see some of the stuff we've been talking about. I don't know exactly what all of these devices are, but could be a temperature to pressure device. You can see some gauges here. Those could be corresponding to um, air temperatures or water temperatures. But you have to go and open this panel to actually look at this stuff. But this whole network of tubing in here, trying to trace all that out, figure out what goes to what, I wouldn't be willing to sign up for that. The second type of controls are what's called electronic, or also commonly called packaged controls. And this means that the equipment you buy comes with some control logic built into the unit itself. So the manufacturer creates the control logic through some circuitry using relays, resistors, capacitors, internal programming. So there still can be some software involved on this, but the big thing is that the manufacturer creates the controls for you. They wire it up inside the unit, and then that just gets shipped to you as part of the package. In these instances, the control logic is mostly locked down, but the customer does have the ability to change some things. Most common thing they can change are, one, the operating schedule of the HVAC equipment and the space temperature set points. We'll come back to that later on. The advantages of electronic or package controls: they're generally pretty inexpensive and they're pretty simple to operate. And the controls that the manufacturer offers is usually good enough for most clients. Not all clients want this, but for most clients, this is fine. This is especially true if there's no central DDC building controller to tie into. DDC controls being the next control option that we're going to talk about. And it can be pretty useful if you have a less sophisticated client who just wants you to give them something and just have it work. The manufacturer gives you the control logic, and the manufacturer has tested that control logic. You know it's going to work. You don't get all of the bells and whistles. You don't get to customize every little thing, but it should work. The downsides: it can be a little difficult to troubleshoot or to try and optimize because that control logic is largely locked by the manufacturer. You get what you get with little room to change things. And so if you have a more sophisticated client, they might want more flexibility. They might want that ability to change things around and optimize things. I guess a way to think about it is kind of like iPhone versus Android. iPhone, the platform is totally locked down by Apple, and you can't really change much unless you jailbreak your phone. Whereas Android, you can change all kinds of things and it's totally customizable. And neither one is better. They're just aimed at different clients. And with packaged options, you might have some issues meeting some of the requirements of the more stringent energy codes. I've run into this in Washington because the Washington State Energy Code is very strict compared to most other locations in the United States. And so, because Washington is so strict and it has certain requirements, sometimes these packaged options can't do what you need them to do. And if you're reading the code in a strict sense, that means I can't use that equipment. And you might need to go to the actual unit itself to either make your changes or to see if you have any alarms that are going on at the unit. This is an example of what that interface might look like. So this little display here would be right on the unit itself. So if this unit was up on your roof, you'd have to go up to the roof to find this. And you could see, if there's an alarm LED right here. So if you have a issue with the unit, that LED would turn on. You'd push the buttons on here and it would probably spit out an error code. And then you'd have to look in the manual, see what that error code means. But you can see there's not a lot you can do here. There's really only 4 buttons on this thing. I would say most onboard controllers are probably a little more sophisticated than this. You'd probably have a little more, a few more buttons, a few extra things you could do, but you might not. This might be all you get. And I mentioned that these controls are often just built with basic circuitry. And that's how a lot of this control logic is built. If this thing is true, do this other thing. So this could be a way that they implement these packaged controls. And this would also be an explanation as to why some of this stuff is locked down, because it's not easy to just go in and change the circuitry of the thing. But there is likely also some software built in. You will be able to change some things, and that's probably more on the software side. But the big point, a lot of this logic is mostly locked down. You get what you get. Hopefully it works. But if you have a unique application where the pre-baked controls from the manufacturer might not be able to do what you need it to do, then maybe you can't go with this option. Which brings us to the last controls option. I mentioned earlier DDC, that stands for Direct Digital Controls. With DDC systems, the control logic is entirely based in software. So it doesn't have the circuitry that we were just looking at. It is 100% software based. It means that your control logic is fully programmed, unique to every building and every piece of equipment. The way this works is the mechanical engineer. So this would be me in my current role as a design engineer. I would write the control logic intent, which is an important distinction. I'm not writing the programming itself. I'm not writing the control logic in C++ or any other control language. I'm writing the intent. It's more of a narrative basis where I say, this fan needs to run when these things are true. It needs to turn off under these conditions, et cetera, et cetera. So I write that intent, and then I give that to a controls contractor, and then they will program it. And this is done on a project by project basis. Very different from the packaged controls option, where every single person who buys that piece of equipment with that controls option, they all get the same pre-built sequence. With the DDC system, every single project is uniquely programmed. And all of this is controlled centrally from a central computer, which means you can look at every single piece of equipment in your building and see what's going on from that one computer. And oftentimes, you can look at that equipment through a web browser offsite. Sometimes our customers will give us access to their DDC system. They'll create a temporary login and essentially give us a guest account that's locked down so that we can't make a bunch of changes. But let's say we just want to look at what their equipment is doing. Sometimes we can do that from our office if a client is willing to give us that info. And that can tell us a lot about what all of their equipment is doing, and we can do that from our office without having to travel on site. DDC systems are very common in commercial buildings. The advantages, they are generally pretty easy to troubleshoot, and if needed, you can modify the programming. So we're no longer dealing with pre-built control logic. Now we might write our sequence in one way, but then find out, well, we didn't think about this unique situation, and now we're having this weird thing happen. we can go in and modify that programming. We can view all of our equipment at a single place, wherever that central computer lives. It's usually within the building, wherever the HVAC technicians are working, but you can also usually access it from offsite as well. You can also trend control points for monitoring. So let's say I wanted to know what was the supply air temperature of this air handling unit for the past 24 hours. I could plot that on a graph and see how my supply air temperature is changing. And maybe I want to graph that against when my heater is supposed to be running. And then I can make sure when my heater turns on, I see an increase in supply air temperature. Or maybe if the heater's broken, maybe I'm not seeing that correlation. I'm seeing the heater try to turn on, but I'm not seeing a rise in temperature. So that can be extremely helpful in trying to troubleshoot equipment and find out what's going on. And we get that remote visibility through a web browser. And it's very important, you can get alarms via email or text message. Versus a package control system, I'd have to go to the unit itself to see that there was an alarm on it, and I might not even know that there's a problem until my space starts to get so uncomfortable that somebody makes a stink about it and tells me to go check it out. This can tell me right away if I have an alarm and allows me to fix it much faster. The downsides, it does have the highest first cost by a pretty wide margin, actually. And that's the first cost. There's also potential subscription costs. Whoever is providing your controls software, they may require you to pay a yearly fee for the privilege of using their software and just for them to provide general support and upgrades and things like that. And once you pick that provider, it's pretty tough to switch. Within McKinstry, we tend to use 3 or 4 different controls providers. They all have their own interface and their own software. And once a customer chooses one of those providers, that's it. They are locked in for the life of that control system because it's very expensive to go in and essentially fire that controls contractor once they are in your building. So this can be a pretty big decision to make. But yeah, once you're in, you're a captive customer. This is an example of what a DDC interface would look like. So this would be one air handler. So we can see we have our return air coming in, our filter. We can see our filter is clean. Normally the way they measure that is they look at the pressure differential on each side of the filter. So a little pressure probe on each side. And as the filter builds up with dirt and lint and everything, the pressure across the filter will start to increase. And you set a moment where if my pressure across my filter reaches this amount, tell me my filter's dirty. And then as soon as you change your filter, the pressure drops again and then tells you it's clean. We're measuring relative humidity of our return air, temperature of our return air. Here's a return fan. We can see the S/S means start stop. So we can see the fan is on. We have a device that proves it's on. That's the status. We can see the VFDs running at 80% speed. We have an energy wheel right here between our return air and our outside air. Recirculation damper so it can pull in air across the airstreams. Mixed air temperature, chilled water coil, hot water coil. You can see what the valves are doing. So our chilled water valve is fully closed and our hot water valve is partially open. A big red flag would be if I open this up and I saw my chilled water valve is open at the same time as my hot water valve? Well, that would be simultaneous heating and cooling, and that would be very bad. There's no reason both of these valves should be open at the same time. Supply fan, same thing, VFD maxed out, and then our supply air temperature, and then this is our duct pressure sensor, because remember, that's how we control the VFD, is based on changing duct pressure as our VAVs open and close out in the system. So we can see our set point, we're trying to maintain 1.85 inches water column. We are actually at 1.89, close enough. But if the actual reading here was to increase or decrease, that would tell our fan what to do. Although I guess in this case, it's already maxed out, so it can only go down. But you can see how much visibility this gives you on this piece of equipment. And you can set up all kinds of alarms to alarm you of certain things. Like on the fans, if my command, if I'm telling it to be on, but my status tells me it's off, send me an alarm. That means my fan is not turning on like it's supposed to. Or if my hot water valve is open, but my supply air is below a certain value, maybe my supply air is only 45 degrees, send me an alarm and tell me that my heating has possibly failed. This just gives so much flexibility, but you can also imagine how much this would cost, because every single thing you're seeing on here requires connecting into this control system to give you this information. And you could have a combination of different control systems. So these types we've talked about, pneumatics, packaged, DDC, they're not necessarily mutually exclusive. You could have a building, in theory, with all three of these controls and have it all communicate. You probably wouldn't have um, multiple control types on any given piece of equipment, but it could be that this wing of the building is on pneumatic controls and this other wing is on full DDC. But DDC systems usually, not always, but usually can talk to package controls. That communication might be limited, but the package controls might be able to output certain things to the DDC system. Like, what is my unit doing right now? Is the fan running? Is heating running? Is cooling running? We might not be able to control when those things are running, but we might be able to at least pull back the status of what's going on with that unit. And you could have pneumatic devices that interface with the DDC through what are called electro-pneumatic transducers. And what that means is you still have all the pneumatic stuff going on that we talked about earlier, but this would take the pressure readings from those pneumatic devices and through these transducers convert them to an electronic signal. So you could still have a temperature sensor, a pneumatic temperature sensor, reading the temperature of an airstream and outputting a pressure. And then if you put this transducer in, you can still read that temperature through the DDC system. So this introduces a potential stopgap for controls upgrades. Maybe you go in, you install that DDC infrastructure first. Maybe the customer doesn't have the money to do the whole thing all at once. So maybe you put in the infrastructure first and then come back later and replace the pneumatics. And for the time being, you just put in these transducers. But the idea ultimately would be to get completely off of the pneumatic system, at least most of the time. So let's talk some basic control strategies: scheduling and set points. The two easiest strategies to optimize control are based on these two things: occupied/unoccupied scheduling and space temperature set points. If you were to look at any control system, these would be the two prime things to check for. I mentioned a lot of building operators. You might be surprised at how little they actually know about HVAC, but most of them are capable of implementing some basic scheduling and set points. This is controls optimization 101. They should be capable of implementing this. It is very basic, but it is also very effective at saving energy. And one thing that's nice is usually you can go in and do these things without needing to replace any equipment at all, which can mean high savings but very low cost. And if you have high savings with low cost, that means the payback will be very quick. Big caveat though, if there's some other reason that they run everything 24/7, if there is some other equipment deficiency and this is their band-aid to fix it, well, this isn't going to fix that issue. With equipment scheduling, the most efficient system is one that is off. The HVAC system should only be operating when people are there. If nobody's there, the system should be off. So if you go out and you find a system that is just running 24/7 for no reason, that is, I see dollar signs in my eyes kind of deal. That is a big, big savings opportunity. If I find that a customer is running their systems 24/7 when the building might only be occupied from 7 a.m. to 5 p.m. Monday through Friday. So maybe we can go in and implement a schedule. Say, we're going to run in occupied mode from 8 to 5 Monday through Friday, and then the system will go into unoccupied mode every other hour of the day. That's an extremely simple schedule you can implement that you don't usually need to replace any equipment to do, and that can save a big chunk of money right there. And for some synergy, you might be able to tie your HVAC operation into occupancy sensors, which might already be there to control lighting. So that could be a very low cost option as well. So you might say, well, my equipment's scheduled to run 8 to 5, but if the room's empty for several hours every day, conference rooms are a big, big example of this. They have these big swings where you have really high occupancy and then everybody leaves and you have at least a couple hours where nobody's in the room, and then the next meeting comes in and they use it again. So there could be these large chunks of time in the day where it's not being used, and you can turn off the system for those periods with those occupancy sensors. There's no reason to run the HVAC when no one is there. And this statement is really more of a general energy saving statement. Figure out how you can turn stuff off whenever we can. The most efficient system is the one that's off. So let's figure out how to make it off for more hours of the day. So the second strategy, talking about set points, usually we have two different kinds of set points. We have our occupied set points for when people are actually there, and our unoccupied set points for when the building is completely empty. And this leads us to 4 different set points that we typically worry about and the typical ranges. We have our occupied heating, usually somewhere in the 68 to 72 degree range. And then we have unoccupied heating, usually 55 to 62. Our unoccupied heating should always be lower than our occupied heating, because when people leave at the end of the day, we want to set back the temperatures to a lower value, because that's going to use less energy the colder we keep our building. Then we have our occupied cooling in the 72 to 76 degree range, and our unoccupied cooling, 80 to 85 degrees. And here you can see our unoccupied cooling is at a warmer temperature. So in the summer, everyone leaves and we allow the building to get warmer, because that's going to be more efficient than trying to keep the building down at 72 to 76. So during nights and weekends, when we're in unoccupied mode, allow the building to get colder in the winter and warmer in the summer. This is going to reduce the delta T between the inside of your building and the outside of your building, which will reduce your heat transfer and reduce the amount of heating and cooling you have to do. When we're in occupied mode, we're maintaining those occupied set points, and our fans are running constantly for ventilation. We always have to be providing that ventilation whenever the building is in occupied mode. And then as soon as we enter unoccupied mode, everything shuts off and our unoccupied set points go into effect. So if our unoccupied heating set point is 55, the heating equipment will only turn on if it actually gets that cold. So remember, we were maintaining our building at around 70 degrees, and then all of a sudden we go into unoccupied mode, all of our set points drop to 55. Now our heating equipment will remain off unless it actually gets down to 55 degrees. Similarly, on the cooling side, unoccupied mode at 85 degrees, the cooling equipment will only turn on if it actually gets that warm. And another way this saves a bunch of energy is the unoccupied mode operation is intermittent. It's only enabled as needed. So this is more of a cycling of equipment, as opposed to when we're in occupied mode, we have to run the fans constantly for ventilation. In this case, ventilation is closed if we're unoccupied mode. And then there's this idea of what's called the dead band, which is an important concept when we're talking about space temperature set points. So you should have what's called a dead band, which is the temperature range between the occupied heating and the occupied cooling set points, in which no cooling or heating is to be enabled. So to put some numbers to that, if our heating set point is 70 and our cooling set point is 75, then if we are in between 70 and 75, then no heating or cooling should happen. That's kind of the sweet spot, I guess. The heating should only turn on to maintain 70, and the cooling should only turn on to maintain 75. If we're in between, the fans just run and the heating and cooling remains off. So a 5-degree dead band, that is required by the Washington State Energy Code. And I think it's actually required by most energy codes nowadays. The reason being, this is to prevent simultaneous heating and cooling. If hypothetically, let's say your heating and cooling set points were both set at 73, then your heating and your cooling systems are going to be fighting each other all the time. And even if they're not the same value, let's say you only had a 2-degree deadband between heating and cooling set points, there is still some fluctuation around those set points. If my cooling set point is 75, I'm not just maintaining exactly 75. It's going to be oscillating around 75. And if you cut down that deadband too small, you can still have those instances where your heating kicks on and then your cooling kicks on, and it's just a constant battle between the two systems. Or worst case scenario, what if your heating set point is higher than your cooling set point? Now you have constant simultaneous heating and cooling where your heating and your cooling systems are essentially playing tug of war with each other. So your heating set point should always be lower than your cooling set point. Next controls concept is what's called economizers. So what if you have a cooling load in your building, but it is cold outside? So you could have a conference room stacked full of people, or you could have a server room full of computer equipment. In those scenarios, do I really need to run my air conditioner? So enter what's called economizers. The general idea for an economizer is instead of using air conditioning, let's just use that cold outside air to provide cooling to the building. This will only work though if we have a cooling load in the building at the same time we have cold outside air available. And depending on your building, there might not be a lot of hours where that is true. Because as it starts to get cold outside, generally you don't really have a lot of cooling load. But you can have those instances like the conference room full of people or a data server room where those rooms might need cooling in the middle of winter because there's so much internal heat gain going on. The first economizer, old-fashioned version, is you open a window. Oh man, it's getting stuffy in here. Let's open a window. Let's open the economizer. Although nowadays, economizers are more integrated into the HVAC system. We have airside economizers, which is also known as free cooling. So instead of turning on our DX or our chilled water systems at the air handling unit, just bring in the cold outside air through the air handling unit. Run the fan, push the cold air through the duct and into the space. The fan, specifically the supply fan on your air handling unit, it needs to run anyway because we have to provide that ventilation. So there's really no energy penalty associated with an airside economizer. All we're doing is providing a higher ratio of outside air. So that's where this term free cooling comes from. We have to run the fan anyway. There's no other penalty that we have to pay. But it might not be doable if you're in a humid climate. If you pump in a bunch of humid outside air into a building, you're asking for mold problems. But in a lot of other areas of the country, economizers are required by many energy codes out there. And they call this an airside economizer because we're cooling down our supply air by just putting more cold outside air directly into it. If we had a basic air handling unit here, if we have a thermostat that says our room is hot, hey, we need cooling, just bring in more outside air. Just open the damper that's going to be in there and just bring in more outside air. And proportionally, we just need to relieve more air in order to keep the building in balance. So airside economizers, generally very simple. It gets a little more complicated with a water side economizer. This only applies if you have a water source chiller with a cooling tower. Only that type of system. if you have that, you can use a water side economizer. Instead of chilling your water through a chiller, which we know takes a lot of power, let's use the outside air to chill the water. So it's called a water side economizer because we're cooling our chilled water instead of the airstream directly as we would with an air side economizer. So to walk you through this, and I'll have a visual here in a moment, a water side economizer, you're taking your condenser water, which as a reminder, that's the side that's going through the tower. Run your condenser water through the tower, let it cool off to a really cold temperature, so 35 to 45 degrees, using that cold outside air. On the chilled water side, bypass the chiller. And instead of going through the chiller, we're going to go to a heat exchanger where the chilled water side can trade energy with the, using air quotes, chilled condenser water. So now we can create 50 to 55 degree chilled water that we can send out and use in our building using that 35 to 45 degree condenser water. This does avoid running the chiller, but you do still need to run all of the pumps. You still need to move all that water through your system. Because of that, because of those pumps, you can't really call this free cooling. In an air side economizer, you can, because all we're doing is running the fan and just introducing more air, no penalty there. Water side economizer, you're still running pumps, so it's not quite free. But most energy codes say water side economizers are good enough. So what does this look like? So here is a basic water source chiller system. So over on this side, this is our chilled water side of the loop. This pink rectangle would represent a chilled water coil. So we're sending water down the supply, going through a chilled water coil where it's cooling down an airstream or doing whatever it's doing. Coming back to the return side, just imagine a bunch of other coils out in the system. The return side comes into the chiller, where the chiller rejects heat from the chilled water side to the condenser side, where it goes through the cooling tower, cools it down, comes back. This is the basic water source chiller setup that we've already talked about. So the way it differs is in an economizer mode, we are adding this loop down here. So I'll go back and forth a couple times so you can kind of see the difference. So we're adding this bypass over here with the heat exchanger. So we're going to bypass the chiller entirely and instead run water through this loop down here. So we run our chilled condenser water outside. So we're going to directly cool that water through our cooling tower, through that cold air, and make this side of the loop nice and cold, 35 to 45. And then through that, we can make chilled water through this heat exchanger. It's not going to be as cold as our normal chilled water operation, but when we're using a water side economizer, we generally don't have a high cooling load anyway. So we're going to bypass the chiller on this side and through this heat exchanger. If we have chilled condenser water on this side and warmer chilled water on this side, well, now we can reject heat through that heat exchanger from the chilled water loop to the condenser loop. So we're still running the pumps. We're still running the tower too. The main thing here is that we're bypassing the chiller. So this map here this isn't up to date, but it roughly shows where you might need to provide economizers. So we can see on the west side of the country, Economizers are generally required if your system is greater than or equal to 5 tons of cooling, where we get more advantage of economizers over here. And then up north and kind of Midwest, you need it for about 11 tons or greater. But then they say, hey, down here in the South, where we're nice and humid, we don't really see a lot of value in having an economizer. So you can see it's very dependent on the climate, on when you might need it versus not. And that's it for part 1. So we'll continue this on Thursday. Any questions on this?